So this video is explaining about standard reduction potentials, how to read standard reduction potential tables, and how to calculate the standard voltage for an electrolytic cell. So this right here is an example of a portion of a standard reduction table. So what a standard reduction table is a table of a bunch of different elements that shows you the voltage associated with their reduction. And so the reduction potential tables follow the same sort of trends that you see in the activity series. So you have the metals increasing from like copper down to like magnesium, the more active metals that increase in reducing strength. And on the other side you have the non-metals increasing with oxidizing strength as you go up, like with the halides, how fluorides are more powerful than bromine. So you can see those trends occur in the standard reduction potential tables. And so that can show you why they sort of work like that. So what you can use this for is to find out the overall voltage of an electrolytic cell reaction. So for the first example, we're going to say we have the reaction between copper 2 plus and magnesium. So the first thing you do is you write the two half reactions. So copper 2 plus. Okay, so we know that copper has a potential of 0.34 volts, and magnesium has a potential negative 2.37 volts. So since copper has a higher voltage, we know that it's more likely it's going to be reduced, and the magnesium is actually going to be oxidized. So when you're calculating, you take the number that's the most negative, and you flip it. So you flip the reaction, so it becomes magnesium solid going to magnesium 2 plus 2 electrons, so it's actually being oxidized, the copper is being reduced, and you flip the sign, so you have 2.37 volts. So then all you do to find the overall voltage is you add two reactions together, so your final reaction is copper 2 plus, your electrons cancel out, plus magnesium solid yields copper solid plus magnesium 2 plus. And to find the voltage, you just add the other two voltages. So you end up having a total voltage of 2.71 volts. So now we're going to do another example of how to calculate the problems when you have a reaction where both the voltages are positive. So say take the example of fluorine and silver. So we start by writing the half reaction again. So fluorine volts, and then silver plus 1. We have a charge of 1, and then this has the results of 8 volts. So first, what we want to do is we want to see which ones we oxide, which ones we reduce. So since both of them are positive in this case, we take the one that has a lower value. So the silver is much lower than the fluorine, so that's what we switch. So we switch the silver to silver solid being oxidized to silver 1 plus an electron with a voltage of negative 0.80 volts. And then, since this has 2 electrons reacting and this only has 1, we want to multiply this whole thing by 2. But when you multiply this half reaction by 2, unlike when you're calculating, say, delta H, you don't multiply the voltage. So the voltage stays the same, even though your overall reaction has more silver in it. So the final reaction is 2 2 silver solid plus F2 gas. Electrons cancel out, and you're left with plus. Okay, so that's your final overall reaction, and all you do is you add the two voltages together, so you have 2.87 minus 0.8, and so you're left with a total voltage of 2.07.